Well, it's a great pleasure for me to introduce Mihalis Kolountzakis from the University of Greece. Mihalis studied in Crete, the bachelor, and then he did his PhD in Stanford, and he moved to Princeton, and then he came back to Crete, where he's professor since 2006. And today he's going to talk about how many Fourier coefficients are needed. Thank you very much. Mihalis.
It's a great pleasure to be among friends again. Okay, so this is the joint work with Effie Papageorgiou, who is also present in the meeting. So this talk concerns the following problem. So we have a family of functions, let's call it script f, which is a parameterized family. So every function in the family is determining, specifying k parameters. And then we look at each object from this collection by looking at its Fourier coefficients. So let's say all the functions are defined on the torus, right? So, and then the natural question is, since the complexity somehow of the function is just k numbers, can we recover the function by looking at only k, or a little bit more, maybe only k Fourier coefficients? So since the functions are restricted, we don't need to look at all the Fourier coefficients of a function in order to determine it. This is the principle. So what we're trying to do here is to, having fixed this family f, we want to find a set of frequencies omega. So if we're on the torus, these frequencies will be integers. If we're in t squared, the torus squared, the frequencies will be part of z squared. But it's important here that we want to fix omega given the family. We are not allowed to change which Fourier coefficients we look at depending on the function. So this is going to be a fixed set omega, and then we look at f hat restricted omega, and this should give us uniquely f back. So this mapping should be 1-to-1. Now, there is, of course, the more practical or more applied question related to this theme, and this is not only to have this function to be 1-to-1, but to also have a way of going back to recover numerically, say, or algorithmically, f given the Fourier coefficients on omega. So we're not going to deal with this at all, although this is clearly very important, but we're not going to talk about this at all. We expect that in many cases, the methods that we are going to show can be converted to algorithmic inversions, but we're not going to deal with it. Okay, so the first problem that I'm going to talk about, which is already very well studied and understood, especially in the engineering literature, is how to determine a measure mu consisting of n, or at most n, point masses on the torus. So we do not know here where the xj are and what the coefficients are. So recovering the measure mu means to recover both the xj and the cj. Okay, and the theorem I'm going to talk about first, and I repeat, this is a very well-known theorem, but I think it's important because we're going to use it quite a bit. So the theorem is that the measure mu is determined by the following set of Fourier coefficients. And it's important that the number of Fourier coefficients we look at is of the order of n, which is about the same as the complexity of the measure. I mean, to determine this measure, you need to specify the axis, which is n degrees of freedom, and then you need to specify the cj, which is another n degrees of freedom if you look at complex degrees, or 2n if you look at real degrees of freedom. So, but the order of magnitude is the same. So we use order of n Fourier coefficients in order to determine this object, which is of complexity, again, n. So the method is so-called Prony's method, which I'm going to show. What is it? How do we start? So, of course, given this representation for the measure, it doesn't make sense to determine xj if cj is allowed to be 0, right? Because then it could be completely arbitrary. So we assume at the outset that all the cj's are non-zero. And we encode the points of the torus as points on the unit circle in the complex plane. Rho j is e to the 2 pi I xj. And then it's very easy to see that the Fourier transform of the measure that we have will be exactly this sum of powers of the rho j. And we're going to encode the roots, the xj or the rho j, which are the same thing, as roots of a polynomial. So we form the polynomial a of z by taking it to have rho j as roots. And of course, when you carry out this multiplications, you will write it out as an ordinary polynomial, and the coefficients will be the Fourier coefficients of this viewed as a function on the torus. Okay, so this is the polynomial. Essentially, we want to determine the polynomial a, because if we determine the polynomial a, we know where the roots are. Therefore, we know where the masses are sitting, and then we can proceed, which is much easier to find the coefficients. So we observe that the measure mu multiplied by the polynomial a is 0. Why? Because a vanishes wherever mu has a point mass. So this is clearly identically 0. Therefore, going to the Fourier side, the convolution a hat star mu hat is going to be 0. Okay, so we are going to reverse this. So if we have a trigonometric polynomial a, which is of degree up to n, and we know that its convolution with mu hat is 0, and we do not have to check everything, but only these values. This is the important thing here. If we only know that the convolution here is 0 for all these values, it will turn out to be 0 for all the values, and the polynomial a will be what a hat will be what we need. So the conclusion is that if we only can guarantee this for these values of the variable L, then our polynomial is what we were looking for. Okay, and how do we do this? So we just write out this convolution, which is going to be this sum. We replace mu hat by its equal, which is this power sum of the rho j. And we, of course, as we always do, we reverse the order of summation. We collect the terms, and what we turn out to have is a summation of rho j to the L times these numbers. Okay, now the rho j to the L, to the minus L, is a van der Waals matrix. If you consider j and L to be the variables of the matrix, it's a van der Waals matrix, which is clearly non-singular because all the rho j are assumed to be different. That's what you need for a van der Waals matrix to be non-singular. So since they are, this is a non-singular matrix, and this is a 0 vector, because this is 0 for all values of L, it follows that these numbers are 0. And since we have assumed that the Cj are not 0, the A's must be 0. So we showed that our polynomial has roots where it should have them. And since its degree is the right quantity, it is our polynomial. And we now have to observe that the only values of mu hat that we used are those shown here, where k goes from 0 to n, L goes from 1 to n. These differences are going to be from minus n to plus n. So you don't need anything else from the Fourier transform of mu in order to guarantee that this happens. So from this information, we can go and recover the rho j. Now the rest is easy. If you know where the masses are sitting, then you observe, again, van der Waals is a keyword here, right? That the mapping from the Fourier coefficients to the values, you don't even need to look at the left half of this data, just the right half would suffice. The mapping from the Fourier from these coefficients to the Fourier coefficients is going to be a one-to-one mapping, because again, it's given by a van der Waals matrix. So you can just invert that and you get your coefficients too. So in the Prony method, we first find where the points are sitting, and then if we know that, it's just an observation that it's a van der Waals matrix we can get from the values to the coefficients. Okay, this much is well known, and so it's probably also well known what I'm going to show now, but it's an alternative derivation of this problem, which is somewhat more general, so and easier to understand, although it's a little less constructive than what I just showed you. So how else could we show that if we know mu hat from minus n to n, it determines the measure? First of all, we do the following trick. We pretend that we know where the masses are. Okay, we pretend that we know where the masses are, but we don't know the CI. Again, we observe that this is a van der Waals system. So if you just examine n consecutive values of the Fourier transform, the mapping, which is this mapping we had before, it's exactly the same, is given by a van der Waals matrix. Here it is, actually. Therefore, we can recover the Cj from the right-hand side of the linear system, and we can determine the Cj. This is exactly what I told you before. It's not really any different. So if we know where the locations are, then we can easily recover the Cj, but we don't know where the Xj are. So what do? It's the following trick, which we're going to use again. We're going to use twice as many as n. So suppose we have two measures, which are at most n points each, right? Two measures on at most n point each, and we form their difference. Now, their difference will live on at most 2n points. Okay, so since they live on 2n points, we know by our previous result that this collection of coefficients, which is 2n consecutive values of mu hat, determines all the coefficients, but all the coefficients of this measure, of the masses of this measure mu, right? And it's an injective system. It's an injective map. So the Cj are all determined by this. So if we assume that mu1 and mu2 have the same Fourier coefficients here, then mu has 0 Fourier coefficients here. So the coefficients of mu would be identically 0, which means that the original measures, mu1 and mu2, were the same measure. So this is a very easy trick. So if you know how to solve the problem with fixed locations, all you have to do is double your size, and you can solve it with variable locations by just looking at the difference. It looks very cheap, but it works. It's not constructive though, right? It doesn't, if you care about inverting algorithmically, this is not in the right direction. Prony's method is fine, but this one is not. Okay, but still, for what we care, this is a very conceptually very easy. Okay, having dealt with the endpoint masses, we now go to a new problem, which concerns the following nonlinear family of functions. Our functions will be a sum of indicator functions of at most n intervals. So we have a number k, which is at most n, and we take an indicator function of n intervals on the circle. We assume they are disjoint, not even their endpoints can be common, and we want to recover from the Fourier transform of this function. How do we do this? All we have to know, this is what we're going to show, all we have to know is n plus 1, these n plus 1 numbers. It's not as in the previous problem where we could actually shift and any 2n Fourier coefficients would suffice. Here we need to know those numbers. So this is the theorem by Courtney, who proved it in 2010 using Blaschke products and some complex analysis machinery. And I'm going to show you a new proof, which is completely elementary. This is everything on this talk. There's essentially no analysis, just linear algebra. So how does this new proof go? So first, we suppose we have two objects of this type. So we have a set E, which is a collection of n intervals, and another set E prime, a collection of a different set of, let's say, different set of intervals. And we assume that they have the same Fourier coefficients for nu goes from 0 to capital N. And we aim to show that there's actually the same sets. Okay. First observation is that for nu equals 0, we get the zeroth Fourier transform of the function, which is the integral of the function. So we know that the lengths, the total lengths of E and E prime are the same. So this is the total length of E, and this is the total length of E prime. And just by looking at the Fourier coefficients of order 0, we know they have equal total lengths. Okay. And what do we do for a nu different from 0? For a nu different from 0, from this identity here, from the Fourier transforms being the same, we know that the Fourier transform of the derivatives of the indicator function are the same. Because this Fourier transform is just nu times this one. If nu is non-zero, you can cancel it from both sides. So you know that the Fourier transforms of the derivatives are the same. And we want to deal with the derivatives because the derivatives are much simpler. If you have an indicator function of an interval and you differentiate it, you got a point mass here, which is +1, and another point mass here, which is -1, which is much easier to deal with, at least for me. So then you look at the Fourier transform of these measures, and you get exactly this, where Zj are the left endpoints looked at on the unit circle, and Wj are the right endpoints of the first set, and Z prime and W prime are the corresponding points on the unit circle for the second set. So our identity of the Fourier transform for nu non-zero is essentially this identity here. Okay, this is true for every nu from 1 to n. And what do we do now is we shift the W primes to the left and the W's to the right. So we get the following. So we're going to get that the corresponding power sums, as they are usually called, are identical. What is the power sum of a collection of numbers? The nth power sum of a collection of numbers is the sum of the nth power of all these numbers. So since here we have the z's and the w primes, which is the left endpoints of the first set and the right endpoints of the second, the corresponding power sum is exactly this that you see here, which is what would arise if we took those numbers and we moved it to the left. And the corresponding power sum on the other side is this, which is what would arise if we took those wj from here and took them to the right. So these power sums are identical for all these values of nu. Okay, so we're going to work with these power sums, which, by the way, are just an instance of what we call symmetric functions. A function of a set of variables is symmetric if it is invariant under any permutation of the variables, and the power sums are clearly invariant, so they are symmetric functions. And now we're going to involve another well-known set of symmetric functions, the so-called elementary symmetric functions, which are often denoted by sigma k. What's a sigma k of, let's say, n variables? You add up all the k-fold products that these variables can make. That's the elementary symmetric functions. And it's very well known that these elementary symmetric functions form a linear basis of all symmetric functions up to a certain degree, if you take them up to a certain degree. And therefore, every symmetric function of degree n can be expressed as a linear sum of elementary symmetric functions up to degree n. So it is well known that every symmetric function can be expressed to the elementary symmetric functions. What we have here is a so-called Newton-Girard formula, very old formulas, which give you a way to recover the sigma k, the elementary symmetric functions, from the si, which is the power sums. If you do this, if you apply the Newton-Girard formulas for k goes from 1, 2, and so on, you will recover the sigmas one by one. S1 is equal to sigma 1, and then you keep going and recover. If you know the s's, you can get the sigmas. So this is a way of going from the s's to the sigmas, from the power sums to the elementary symmetric functions. But I want to emphasize here that even if we didn't know of the Newton-Girard formulas, we could easily do the same thing by just observing that the power sums are linearly independent. If you take them up to power n, are linearly independent. Their number is the right number. Therefore, they're also a basis of the same space of symmetric functions of order up to n. Therefore, every symmetric function can be expressed as a sum of the power sums. So if you know the power sums, you know the symmetric function, the elementary symmetric functions. That's all we care about. So our equality of power sums that we had here, this equality of power sums for all these values of n translates to the same equality of the elementary symmetric functions for the same values of it, of nu, I'm sorry. So all these elementary symmetric functions are the same. And what do we do next? We actually want to go and remember that the z's are, their number is n, which is less than capital N. And the w primes, their number is n prime. This is, so the first set consists of n intervals, and the other set consists of n prime intervals. We do not a priori know that these are the same, but we do know that both of these numbers are up to capital N. So we want to have up to that many intervals. So we really want to extend this identity of symmetric functions. We want to extend it beyond capital N up to this number, which is usually higher. And how do we do this? First, we'll observe that the top elementary symmetric function to the rightmost of the series we want to go, they're actually the same. They're identical here, and we don't need much for this. All we need to observe is that if we write what this means and we collect the z's and the w's together to the left and the primed variables to the right, we get that this identity here is equal to this product. Now, what is this product? For each, let's say for z1 divided by w1, this is the angle of the first arc. And you multiply all these angles together. So what you get here is the total length, e to the total length of e to the 2 pi I total length of the set E. And this is the same thing for the set E prime, but we know from the zeroth Fourier coefficient that these are the same. Therefore, we know this identity, and we know that the elementary symmetric functions at the top, they are identical. So what we have here, the following situation. We have the elementary symmetric functions up to capital N being the same, and also a little farther away, these elementary symmetric functions are the same. And we want to fill what's in between. So we have the numbers up to N. Here's N plus N prime. We would like to fill the gap in here. And how do we do this? We remember that our numbers are unimodular. Therefore, the conjugate of the sigma k is just sigma k of this. And we reorder things here a little bit, and we get this easy identity where the denominator is that top symmetric functions, which we know is the same for the prime case and not. And on the top, we can use k equals 0, 1, and so on to descend from n plus n prime to n plus n prime minus 1, in which case you would have sigma 1 here, which is known, and this is also known. Therefore, you also know sigma at n plus n prime minus 1, then you get minus 2, and so on, and you get them all. You get them all. And so you get that sigma nu will be determined by the values that we know for the intermediate values up to this one. And therefore, we know that the elementary symmetric functions are identical up to the maximum one. You cannot have any more than that because the number of variables is n plus n prime. But the elementary symmetric functions, why do we use them? Because they are, if you have a polynomial with roots at z, at the points of z and w prime, the sigma nu are the coefficients of the polynomial. So since the coefficients are the same, the roots of the polynomials are the same, and the roots are the same. So what we get is that this set, or rather a multiset, because you could have repeated roots, this multiset is the same as this multiset, because they are roots of the same polynomial, but they may be mixed, they may be permuted. Okay, and the last observation is that none of the wj prime can be matched with the zj prime because they're by definition different. So all the wj primes can only be matched by the wj, and all the zj primes can only be matched by the zj. So what we got is that the left endpoints, the z's, are all the same, and the right endpoints are all the same. This means that the two sets are the same. Okay, and so this is the proof of getting the two sets, which are each of them a union of at most capital N arcs, being the same just by identifying their Fourier transform on the value 0 through capital N. Okay, so this is an alternative proof of Courtney's theorem. And now we go into the more interesting part of the lecture, the more essential, perhaps, part of this lecture, and the more open-ended part of the lecture. So what is the problem here? Now we go to t squared, the torus squared. So we're going to have n points on the torus squared, denoted by u, u1, u2, and so on, each of them with a coefficient. So the points are unknown and the coefficients are unknown, but they are up to n. And we want to find a set of frequencies which will now be part of z squared, such that if we know mu hat on these frequencies, we can determine mu completely. And again, I emphasize that this set omega should be the same, depend only on capital N, on nothing else. You are not allowed to start looking at the Fourier coefficients. Let's say you look at a point here, you see a value, and you look at a point there, you see a value, and then depending on what you already saw, you might decide to look here or there. This is not allowed. People have been doing this and they have been getting very good results, but it's a different problem. So my problem is to fix the omega for all. Okay, and let's see what we can do here. First of all, let us observe that if we take the Fourier transform of our measure, but we only evaluate it on one axis of z squared, on the x-axis on z squared, then we get this sum. The y's are not going to play any role here. So let's denote with capital U the points uj, where the masses are located, and let's denote by capital X the x coordinates of these points. So x is a set, and capital U is also a set. Capital U projects to x. And then we define a measure nu on the line as follows. We take the measure mu, which sits in 2 dimensions, and we project it down to the axis. We collapse all the measures we see, we push them down on the axis. This will give us a measure nu on the real line. And it's very easy to see, but just looking at this, that the mth Fourier coefficient of nu is the m,0 Fourier coefficient of mu. Now, what can we do now from the one-dimensional problem is that nu, the measure nu, which is located on at most n points, we can recover it by looking at the Fourier coefficient of nu from -n to n. This is the Prunier result. That's the first thing I told you today. And because of this identity, we can recover by looking at this row of coefficients, we can recover the set x and the corresponding coefficients, which are these numbers here. So this coefficients and this x. And if it so happens that each x corresponds to a unique y, so above each x in this picture, you have only one y sitting over it, then you know everything already. Because by the application of the one-dimensional method, you know this sum. Well, if this sum consists of just one point, you know the coefficient sitting over x. What you still don't know is where y is, where the corresponding y, the yj, right? But we now look at these Fourier coefficients of the two-dimensional measure, which easily we can see to be this power sum. And again, by the one-dimensional result, which would correspond to points sitting on xj with these Fourier coefficients, we can recover the Fourier coefficients of this measure. So the Fourier coefficients of eta are exactly these numbers. So since eta lives on n points, we can recover these coefficients in parentheses by looking at only these points, n consecutive values of the Fourier transform, because we know the xj are. So we get those quantities, but Cj was already known because of the unique assumption here. We just divide and we get this number. So we also get yj. So what have we done so far? We have proved that if the two-dimensional situation is essentially one-dimensional, so you have a line, say the x-axis, where everything projects uniquely, then essentially we apply the one-dimensional method a couple of times and we get our result. Okay. So what's the next step? is to relax this assumption of uniqueness. So again, this is what we proved so far. We are assuming that the points project uniquely onto the x-axis, and we use this data that you see here, which is, again, order of n data. It's about 2n or 3n. And we get our results under this assumption. And the great open problem here, which I'm not going to close today, is order of n sufficient? Can one find a set omega of size order of n, which can uniquely recover this two-dimensional measure under no assumptions on projections like this? Okay, and again, we want a fixed set of frequencies. This is the open problem that will remain open after this lecture, but we're getting close. All right. So let's do the next reasonable thing to do. So we can do with the assumption that everything is uniquely projecting down to the x line. What if we assume that every point on the x-axis is the image under projection of exactly k points? So here in this drawing, I have exactly 3 points of the set U sitting over each x. Okay, and I want to recover the uj and the cj under this extended assumption. How well can I do? So the same notation as before. U is everything in the 2 dimensions, and capital X is the set projected onto the x-axis. And now we're going to have a measure sitting over each x. So we'll look at the line going through x, and we're going to have k points here and some coefficients on every point. These will make a measure on the x-axis, on the y-axis, I'm sorry. And we call this measure lambda x. So lambda x is a one-dimensional measure. It's the measure sitting over each x among the relevant x points, which are this set. And we would like to recover the points x and the measure lambda x. This is the information we're after. So we're assuming that lambda x has at most k points. For exactly k points, it doesn't make much difference. And then we evaluate the Fourier coefficients of mu at a general point, and we observe that we can, in fact, write a sum over x's as a one-dimensional. It would look like the Fourier transform of a one-dimensional measure, where the coefficients are the lambda x hat of n. It's just an observation here. Okay. And what do we do then? We're going to use the one-dimensional result again. We're going to use it several times. So for every fixed n0, so this point we fix, for every fixed n0, if we take all this data for varying m from minus n to n, we will determine exactly this measure. Why? Because this measure sits on at most n points. And the one-dimensional result tells us that its Fourier coefficients determine it. So what do we determine? We're going to determine all the coefficients and all the x's, but be careful here. We're not going to even see the x points for which the projection is 0. Okay, so one needs to be a little careful here, because in this projection, you might have points here, but when you project down here, you might get 0. And this you will not see by these points alone. Okay, you need to know that some of the Fourier coefficients is not 0. So we apply this trick for allowing the y-coordinate to go from minus k to k. And what do we get from this? We are going to, by applying this one-dimensional result on the lambdas, we are going to determine the lambda hat of n and the x's, but we're only going to see an x if it shows up in some of those rows. Row means fixed n. So we're going to see an x if some of the Fourier coefficients of lambda x hat is non-zero. It will show up at some stage. For which x does this happen? For all of them. It happens for all of them, because these numbers determine lambda. Why do they determine lambda? Because lambda sits on at most k points. So you only need to look at minus k through k Fourier coefficients. So if these are all 0, then your measure lambda was 0 to begin with, so it wasn't there. So for every point in the projection, it will show up in some of those, for some of those n here. So everything is determined. We determine every x and every lambda sitting over it. And how much data did we use? We used these numbers. And these numbers are about n times k. This is how much we used. Is this good or bad? Well, in the worst case, k can be as much as n. For instance, it could be n over 2, right? In which case, this method gives n squared. So what we know for unrestricted inversion means no assumptions on how our set looks like. We can recover with n squared points. And from what is my understanding by looking at the relevant literature, which is mostly engineering literature, this had been the best known general result with no restrictions. And what we're going to do next is lower this n squared to n log n, which is quite an improvement. So what we're going to show, it's actually a very, very specific set that we present. So we're going to show that there's an omega in z squared, a set of frequencies of size n log n. I'm going to show you precisely what omega is, which is sufficient. It will allow me to determine every measure on n points on t squared. And one such data set, which I would like to call data 2n, is what arises from the following definition. Data n is all the points that you see here. So you go from minus, so this is y equals 0. So you go from minus n to n for 0, minus y equals minus 1, and y is plus 1. You get from minus n to n. And then you start reducing how many you take by dividing by r. So in the rth row, you take n over r points. So this line here is n over r. This will be sufficient to determine everything. And how many points are these? Well, there will be n plus n over 2 plus n over 3 plus n over 4 plus n over n. That's n log n. Okay, this set of points is n log n. And we're going to show now that this is enough to determine everything. And how do we do this? This is the basic lemma. So suppose we have a measure like the ones we're looking at, but suppose also that we know u, we know the locations, okay? It's the same trick that we did right after I gave you the proof of Prony's result, where I gave you this alternative method. So I'm going to show in this lemma that data n, if I know u, data n, which is the frequencies of these points, data n determines mu. And if all the Fourier coefficients in this set are zeros, then so will be mu. And why is this enough? Since we don't know u, same trick again, we double everything. So if you have mu1 and mu2 at most endpoint masses, and if they agree on data 2n, then these are equal. Why? Because the measure mu1 minus mu2 lives on 2n points. And you cannot, and if you evaluate the Fourier transform of this measure on this set by the lemma, if you read all zeros, it has to be the zero measure. So mu1 is equal to mu2, which is exactly what we want. So you can almost immediately get rid of the conceptual problem of not knowing where the points are located by doubling the parameter n. That takes care of it. So we're left with proving the heart of the matter, which is the lemma. Okay. And let's see how we go about this. So as before, this is our picture. We have a measure living on these points, and we project it down. We get a collection of x's. And above every x, we have a measure living on this vertical line, and which we call lambda x. And we obviously want to determine all the x's and all the measures lambda x. Now, remember, we know the locations. We know where these x's are, and we know how many points are over each of them and where they are. We only seek the coefficients, right? Okay. So we're going to determine lambda x. Now suppose that lambda x has t points. So suppose that above this x, we only have t points. Then by the one-dimensional result, it's enough to know these numbers. Okay, we'd like to know these numbers. By the one-dimensional result, this is lambda x has t points. That's enough. So we partition our set x are those projections here, into x1, x2, and so on, where xr is those x's with r points sitting over them. And the crucial observation here is that if you take the sum of these, how many points are in xt plus how many points are in xt plus 1 and so on, this is at most n over t. Why? Because above each of those x's here, you have at least t points. So t times this number is at most n, which is the total number of points. You divide by t and you get this. Okay, so xt and above is at most n over t points on the x-axis. Let's first determine the part of mu sitting over x1. We know where x1 is, and we're going to find those measures sitting over x1. So for x1, since x1 means that we have a point x with just one mass sitting over it, just one. These numbers, again, by the one-dimensional results, these numbers are enough to determine lambda x if x is in x1, because it's just one point. Now, where do we get these numbers from? We get them from this. Actually, if we want to get lambda xn for n up to k for us is 1 here. If we want to get all the lambda xn for n up to k, then we look at those numbers. This is exactly what I did in the previous result with kn points. We proved that these numbers determine lambda x hat of n for these n. So from this set of data, we only care to go up to -1 and 1. From this, so we're only going to live n go up to 1. How much data is this? It's about 3n, because the values of n we have here is -1, 0, and 1. And m goes from -n to n. Actually, it's twice that. It's 6n. Okay, so it's a linear number in n. And these numbers will actually give me everything in x1. We know where the points are, and we know now the measure. Okay, now we have determined x1, and we isolate the measure, which is on x1, and we subtract it from mu, and we get another measure. Mu2 is the original measure minus whatever is sitting over x1. Now, in this measure, if we project it down, we get something living here, because all the x1 points have been removed. So everything projects to at least 2 points. Therefore, the size of the projection will be n over 2 now, because of this inequality I told you before. Xt and onwards is less than n over t. So I apply this for t equals 2. And how do we determine this set mu2 on x2? We're now going to isolate the part of x2 only. Okay, for each point in x2, we need to know these numbers. And how do we get these numbers? From this set, from this set, okay, from this collection of Fourier data. How much is this? Well, this is n over 2 in the x direction and from -2 to 2 in the y direction. But part of this set we already have. Okay, whatever corresponds to little n from -1 to 1, we already have at our disposal from the previous step. So we only need to add those Fourier coefficients, which are for n equal to -2 or +2. How many are they? N over 2 for one and n over 2 for the other. That's twice times n over 2. So we also determined x2, which is the part of the measure projection containing 2 points in every lambda. We also determined x2 at the extra costs of n over 2 times 2. And the next step is to determine x3. Again, we subtract mu2, which is whatever sits on over x2 from the measure. We now have a measure mu3, which projects down to this set. And this set now consists of at most n over 3 points, even less. And to determine this set, we only need to know for each x these numbers. And how do we get these numbers? Well, these numbers we get by looking at these. And again, most of these we already have. What we don't have is, okay, this should be 3 here. What we don't have is what comes for n equal to -3 and +3. How much is that? N over 3 for -3 and n over 3 for +3. That's, again, twice times n over 3. So we had n for the first step, twice times n over 2, then twice times n over 3, then twice times n over 4, and so on. What we get is twice n times 1 plus a half plus a 3 plus 1 over n. That's n log n. Okay? That's all we need, n log n points. So as we determine more and more complex parts of the measure, we need to look at this shorter and shorter set of Fourier coefficients. Why? Because the points with a lot of stuff over them are few. That's the essence. So you don't need to look at too much. So continuing in this way, we determine everything, and that finishes the problem. And the question that remains in this problem, which I think is the most important of this paper, is that can we lower this n log n down to n? So this is a summary of what we did. We looked at the first problem, endpoint masses on T, which is well known. I just reminded you what's known. This is n intervals on the torus, which I gave you a new proof of a result of Courtney that n, the Fourier coefficients from 0 to n are enough to determine. And this is a completely new result, which I think is much better than what's already known. And I want to repeat here that you want a fixed set of omega that does not depend on the data as you go on. It's a fixed set that should determine everything. And that's it. Thank you for your attention.
Thank you very much, Mihalis. If there are any question or comment?
May I, Jorge?
Yes, of course.
Thank you, Mihalis. Very nice talk. Very deep, everything. Has this something to do with Bochner-Herklotz theorem in the sense of characterization of the Fourier, of the characteristic functions of probabilities? Can it be used for because it seems to be maybe you can approximate any distribution by Dirac deltas, any probability distribution by Dirac deltas, and then use your estimate, your algorithm to do that, to find ways to recover the probability as a weak limit or something like that of combinations of Dirac deltas.
I don't think so. I think these what I just told you is really linear algebra and nothing beyond that. I mean, there's absolutely nothing beyond that. I find it very hard that it has anything to offer in the question you ask, because there's a lot of subtlety there and analytic phenomena that cannot be just captured by this. And this is everything I told you about is a finite thing about numbers.
No, right, but it seems possible, perhaps, because the difference, the Bochner-Herklotz adds the condition of something like that. The characteristic function has to be positive, definite, or something like that. That perhaps is a particular case when your Cj's, your coefficients are all non-negative, which also is linear algebra in some sense, but I don't know.
Right. Well, perhaps. I mean, maybe this result tells you that you only have to look at the first. So if you have a measure which is a collection of endpoint masses, then what this says is that to determine if it's a positive measure, you only have to look at the Fourier transform from 0 to n. This is perhaps what you're saying. Which it does, of course it does. Now, if this can be helpful in some questions of probability, I really cannot guess at this point. But it certainly tells you that you can determine positivity by looking at n points.
Thank you, Mihalis.
Thank you for the question.
Is there any other question or comment?
Is it common that in engineering and these examples you have several points for a fixed x in the product of the two torus?
My guess is that if you're looking at this problem from a very practical point of view, then what you would probably do is just take a random direction and project everything to that. And you could be the unluckiest guy on earth if it happened to have more than 1 point. So I'm sure the engineers are doing things like that. And they consider their life, happy, and we don't care about questions that we ask here. But we're mathematicians, so we like to ask questions which sometimes have no practical effect.
Thank you.
You're welcome.
Is there any other question? Okay, if not, we thanks again to Mihalis for his wonderful talk.
Thank you for bearing with me.